deconvolution, especially large survey image deconvolution. And this work has been done in collaboration with many people. And here, Morgan Schmidt, who is PhD now in my group. Morgan is here, so you can raise your hand, Morgan. Yeah, so an equation on optimal transport is for Morgan. Sam Ferrance, who is my colleague at CEA. Fred, who is a former PhD student. Rebecca, intern. Alexis, intern. And Florence Sureau, a colleague of, at CEA. So my talk will be in 3 parts. First, a small introduction, what is deconvolution and what the problem is large images. And then I will show you how we perform PSF field recovery, especially for the Euclid project. And finally, the last part will be how to plug this PSF field recovery in a deconvolution technique. So large image, I think everybody here have seen this kind of images with many stars, galaxies, and we are interested mainly in finding all the galaxies, measuring the shapes, the flux, and all these things. And for some of the studies, we need to deconvolve the images. And this is, for instance, the case in weak lensing when they want to measure the shape. Some technique like called meta-calibration for people who know, they apply first a deconvolution on each galaxy which is detected. So if you want to study the morphology as well, you may want to remove the effect of the PSF before comparing galaxies together. So I think people know exactly how this deconvolution technique. First, you observe a galaxy, you have the point spread of the instrument, and then this is what you get on your data. So it's pixelized, and it's noisy, and it's blurred by the point spread function. If you observe a star, then you get the point spread function of the instrument, and it's pixelized plus some noise. So what is interesting is, if you look at the star in the image, it provides you a measurement of the point spread functions. So you can use a star to estimate the point spread function of the instrument. So deconvolution. So now you assume that you know the point spread function here. So h is the point spread function. X is the image you want to recover. Y is your data, and you have some noise. So this is a really standard problem in astrophysics and in many other fields. And this is well known to be an inverse problem, which is ill-posed, and when it's ill-posed, you need to add what is called a regularization. Regularization means you add some constraint on the solution, and this constraint will define your, the fact that you have one unique and stable solution, and depending on the constraint, then you have a different solution. So the quality of your solution will be highly dependent on the constraint you plug in your system. So the first approach is you have some physical knowledge on the object. For instance, if X is a Gaussian random field or any kind of knowledge, then all the Bayesian techniques, for instance, belongs to this class. And here in this room, we have 2 famous Bayesian guys, and they will consider that the right way to go is to use these kind of techniques. And what is nice with Bayesian people is they trust more the model than the data. So even if the model is not perfect, that's not a real problem. So the second approach is to make what you call X learning. It can be dictionary learning, it can be machine learning, it can be deep learning. And here is another way to consider the knowledge. You consider the knowledge through a set of training data. So you assume that you have a training data set which is representative of your data, and you try to capture the knowledge on the data from the training data set. And if you do that, then you arrive at these deep learning techniques, and then you can find a way to regularize your problem. And the last one, which is more on looking at the data. So here you don't have any training set. You have some knowledge on the distribution of the pixel of the data, either directly in the image or in a given representation space, like Fourier space or a wavelet space or any kind of space. And here, these constraints are much weaker than in the 2 previous cases, but they come for free. So depending on your problem, you may prefer one or the other of these techniques. There is no dogma here, and depending on the problem, really, you have to choose what is the best. And there is no, I don't think there is any way to decide from the beginning which approach would be better. So for the deconvolution, there is an additional problem, is the point-spread function is also varying spatially. So if you look at different stars in an image, here or here, they look very different. So the problem is also to find the point-spread function everywhere in the image, or at least at the position of the galaxy, because it's the galaxy that you want to deconvolve. So the problem also is more complex than that, because there is also a wavelength dependency, and the PSF is varying with the wavelength. So what you observe, when you observe a star, in fact, you have the integral over all the wavelengths, which are weighted by the ACD of the star. And you observe the integral of that, and this is what you get. So it's quite a complex PSF modeling that we need. You have to take into account the undersampling of the PSF in the case of Euclid. It has to take into account the wavelength dependency, the spatial dependency, and the time dependency. So all these effects has to be taken into account if you want to recover the PSF field from the data. So at this stage, we have reasonable techniques working for spatial dependency and undersampling. We start to have some techniques very preliminary for wavelength dependency, and we don't have anything for time dependency. So that's the status of our work, and I will show you now what we do exactly. So the state of the art for this domain is really the work by Emmanuel Bertin at EAP. And his software, I think, is used by most of the big projects, actually. And in his technique, he just assumes that the PSF at a galaxy position is an interpolation between several PSF at star position. By a simple linear interpolation plus a regularization term, then you can find an estimator of your PSF. And that's really the technique that is the most used in the big projects. So in the second part of the project, I will show you now a different approach for doing this, which will be using matrix factorization, Laplacian graph, and sparsity. And for the wavelength dependency, it will use optimal transport. So we will try to plug all these techniques in one single software in order to get a solution to this problem. So some notation now. So we have many galaxies, many stars. And from these stars, all together, we want to estimate the field. So we will write one image of a star as a single vector, and then we have a matrix for all the stars you are looking for. So these are upsample stars that you want to recover. You have a degradation matrix, and this is the observation that we have here. So you can write the problem this way. So you have this term to minimize, and that's the matrix formulation that we have here. So this is a very, very ill-posed problem. And obviously, we had to add a lot of constraints to solve it. So what kind of constraint can we add which are reasonable to solve this problem? So the first one, we can consider that the PSF, the point-spread function of the instrument, is positive. There is no reason to believe that there is some negative value. We can have a model which is a reduction technique where we consider that each point-spread function is a linear combination of what we call eigen PSF. So we can consider that few PSF, eigen PSF, are very good to represent any stars in the field. So it's a low-rank constraint. We can consider that each PSF has some kind of smoothness in it. It's not a random noise. So we can add some constraint here. And also a proximity constraint. Two stars which are close in the field, two PSF which are close in the field should be quite similar. While if they are far away, they can be very different. So we have to find a way now to add all these constraints in a single formula. So the first thing we can do is matrix factorization. So we will assume that this PSF matrix can be separated in two parts, SA, and S will contain the eigen PSF, and A is another matrix. So, for instance, here the distribution along a line of A will represent the weight of a galaxy above the weight on an eigen PSF for a given star on all the fields. So somewhere the distribution along a line here will provide an information on the smoothness of the PSF field. So doing this, we can again make a matrix factorization here using alpha and V transpose. And V transpose here can be seen as a kind of Fourier decomposition, but on the graph of PSF. So to explain better what I mean, is we can assume that each star is a vertex of graph. And now, from this, you can build the Laplacian graph, which is defined by this relation. And you can compute the eigenvectors. You can make a SVD of this Laplacian graph. And doing this, then you get this VT. So coming back to the previous equation, so now we have VT, which is defined, and which depends only on the position of stars in the field. Okay, so this is a fixed. And what we need to find is S and alpha. Okay, so now S on each column is an eigen PSF. So we can assume that S is sparse in the wavelet space. So we have a L1 norm on the eigen PSF. And we have this term. So what you have to find is the coefficient of S in the wavelet space and this alpha coefficients. So the problem to solve, plugging all together, we have a fidelity term, which is here. So you have to find S and alpha. And S is sparse in the wavelet domain. You have a positivity constraint, and you have a smoothness constraint on the alpha coefficient, and which will be just the L0 norm of this alpha coefficient. And using proximal theory, we know exactly how to solve this kind of techniques. I'm not going to enter in the details, but you can really solve this equation. And when we have this, so we have recovered the PSF, we want to have the information at the galaxy position. And for this, we just have to add a vertex at the position of the galaxies, and then you can make an interpolation on this alpha coefficient using any technique like RBF. So now we have a way to build the manifold of the PSF in the field, and from this manifold to interpolate at any location the PSF at a galaxy location. So I will show you some results using Euclid simulations. So we have the Euclid team has derived using a real optic modeling PSF at different locations of the field. So we have used this 500 PSF, and we have derived some metrics which are either the mean square error or the ellipticity error. And this is the kind of result we have. That's just visual results, where we have here the true PSF, here what PSFX will recover, and here what this technique recover. So not to get some quantitative numbers, so we have here the mean square error, and you can see that there is an improvement by a factor of 2 in terms of mean square error. And more interesting, we have also used the Paulin equation, which derive from the error on a PSF, what will be the bias on an ellipticity measurement. And doing this, we can estimate the bias using PSFX and RCA. This is the additive bias, and in both cases, we have a slight improvement using our technique. And in case of for the multiplicative bias, we have an improvement of 20%. So here we are for the spatial dependency. So this is good for monochromatic PSF, but we don't take into account the wavelength. So here we have, starting 1 year ago, especially with Morgan, but also Rebecca, who is intern, came and helped him to do it, how we could use wavelength, the optimal transport, to capture the variation of the PSF along the wavelength. So the reason why we didn't want to use standard techniques for the wavelength dependency is that the behavior of the variation of the PSF is a dilation behavior, right? The PSF dilates with the wavelength. So using a kind of linear decomposition like SVD or wavelets decomposition to try to capture this variation is not good at all, because then it's very hard to capture a dilation using simple linear decomposition. So here we try to use this optimal transport technique, and for people who don't know, the optimal transport technique is a way to calculate the best way to transport a distribution to another one. And then you have a cost of the transportation, and you optimize this cost, and you obtain your new distribution. So we first try to see if this kind of idea was completely crazy, or if you can really capture a variation of a PSF. So the first very toy model example we did, we use two PSF in two directions. So this one and this one. And we try to see if the transport could capture the evolution of the PSF when there is only an orientation, which is the difference between the two. And we did the same with the linear interpolation, and we see that the linear interpolation does not capture at all the variation of the orientation, while here you see that at 90 degrees, here, the optimal transport captures the PSF, but not the linear interpolation. So having the two extrema, the optimal transport were able to find blindly the variation in angle of the PSF, while standard techniques was not able to do it. So if you do this on the distribution, imagine you have two distributions now here, and you want to interpolate between the two. If you make an interpolation, you get this one. Okay? So imagine that your first distribution is people who are very high and people who are very small, and then you want to see people who have the medium size, then you will get this kind of distribution. So the interpolation doesn't provide any interesting information. Now if you replace this Euclidean distance, which is related to the interpolation, by a Weissenstein distance, which is the distance which comes in naturally in optimal transport, then you end up with this equation to solve, and now the interpolation is this one. So you go from this interpolation estimator to this one. So it's a completely different way to estimate an interpolation. And you have all the, because it's a transport, and you can stop the transport at any place between the two distributions, and you can estimate the interpolation at any point. So very interesting technique, but very costly. So the first experiment we did, we had no hope at all to try to use it one day in Euclid. So it was interesting, but only from the integral point of view. But thanks to Morgan and his very nice paper, we now have a techniques which break down the cost using a regularization term using the silicon iteration. So I'm not going to enter the details, but now we have a technique which is at least reasonable and can be used in practice. So we could make some real tests with real Euclid PSF, and to see is taking the two extrema, can we really capture the intermediate PSF? And so we did this experiment, and we took only the two extrema, and we could recover with a very good accuracy all the intermediate PSF. So this was very encouraging, and we try now to plug this into the previous framework, which starts to be a bit complicated to explain now, but here we just replace the fidelity term by using, instead of having one PSF, you have the two extrema PSF, and you have to estimate the transport. So this, plug in all of this together, then you can now reconstruct completely PSF, take into account the wavelength dependency. So this is very preliminary results, but it starts to work, and we hope that in 1 year from now we can show more definitive results with real measurement curve on ellipticity and this kind of thing. So now we consider we have a way to estimate the PSF, and the question is how to use it for deconvolution. And we have this problem of deconvolution. I come back to that I explained before. So we have y equal hx. X is a big image. Y is a big image to solve. Y is a big image. So it's a thousand and thousands of pixels. So it's quite hard to deconvolve an image like that, especially if the PSF is space variant. So h is completely huge. So making this kind of deconvolution is quite complex. And what people do normally is using sparsity. And here it becomes really, really problematic because of the size of the matrix. You cannot use FFT to diagonalize the matrix because it's space variant. So what we can do? So what we can do is first, we are only interested in the galaxies. So we could not try to deconvolve the whole image, but only detect the galaxies and to deconvolve them separately. And the second thing we can do also is some galaxies share some properties. So we can also estimate, in the same way as the PSF, we can also estimate there is a kind of intrinsic manifold, and we can use a low rank constraint instead of the sparsity constraint. So this is the work we have done with Sam and Fred, and we have compared this idea of deconvolving only the galaxy in an image by estimating the PSF by the technique I showed you before, and then comparing low rank and sparsity for the deconvolution. So we end up with this, again, proximal theory for minimizing. So this is really technical, so I'm not going to details here the technique, but it's quite easy. In fact, it's few lines of software. It's not complicated to implement. And we use the same kind of galaxy we had before, and with several noise level, and we apply this technique. And here what we can get, so that's data, sparse recovery, and low rank. So they are quite similar. So we have some plots to show the results. And here what we see is the PSNR is better for low rank. And we have played also with the number of galaxies that we need to have the low rank becoming better than sparsity. And as soon as we had 10,000 galaxies, low rank became better. So because then we can better capture the intrinsic properties of the galaxies. And this has been published. And the situation is, can we do better? And this is on the ellipticity measurement, and we get the same kind of plots where you have low rank better than sparsity. So that was also very interesting for me because I've been working with wavelets for years and years, and it was the first time I saw a technique was better than wavelets for deconvolution. So we wanted to expand a little bit this technique and to see if there was other way to do better. So we have put a subject for a student for an internship, and if you want to have a student, then you have to put deep learning in the subject, otherwise nobody is coming. So this is what we did, and and what we try to do then is to compare this kind of technique with deep learning using still space variant deconvolution. So the first thing is how to make the training, and this was not clear because if you have to make another training every time you have a different PSF, then it will be much too costly. So there is no way to do it. So an approach that can be used is something which had been done also using wavelets many years ago. It was called wavelet-Waglet decomposition, is to first apply a kind of deconvolution of the data, but with a very, very poor regularization. So really letting all the high frequency coming up, and then perform a denoising on the deconvolved image. And this wavelet-Waglet decomposition was using wavelets for this step to make the denoising. And here what we propose is to use deep neural network for this deconvolution part. So a standard deconvolution, pseudo-inverse plus a few small regularization, plus deep learning technique. So Alexis Lechat came for the internship. And what is good with the new guy coming just from the school is they know much better than us on the deep learning techniques. So he proposed what he called, after many investigations, a dense exception U-net. And this is the shape of the neural network. And what he called dense block is this kind of layer where there are some kind of connection skip connections and concatenation. And at the end, he got some very interesting results where he could show that this Ticonet techniques was working very, very well and providing some very interesting results, especially if you compare to sparsity or low rank. You can see that the quality of the image are very nice. And this is another one with very true galaxies this time. The first one was model galaxy. And again, the T-connect technique was working quite well. And if you look at the numbers, in terms of mean square error, then it provides better results. And also, once you have trained the data set, I don't need this, you need only 3 minutes to recover. So it's extremely fast. When the training is done, in 3 minutes you can deconvolve 10,000 galaxies. So it means that this kind of techniques can really be considered for deconvolving large image surveys. So that's something that I think we should think in the future. And in terms of PSNR with the standard, here we have the noise standard deviation. And here we have the T-connect results. We have tried several, so this was another one which was not providing as good results. So that's the reason why I show you only the T-connect. But again, both for the PSNR and the ellipticity measurements, the deep learning technique was doing better. So in 2 years, I've seen wavelets beating all techniques for 20 years, but in 2 years, I saw low rank techniques doing better than wavelets and deep learning techniques doing better than low rank. So that was very, very exciting. So my conclusion of this talk is we have introduced new mathematical framework for this problem of PSF recovery. This framework includes graph Laplacians, matrix factorization, sparsity, and optimal transport. All together are very good to address one specific problem. And all together, they find a very nice tool to derive the PSF field. It's not finished. There's a lot of work to be done. First, to complete the software for taking this wavelength dependency and getting some conclusive results. And finally, to take also into account the time dependency, because it's a 4D problem. And for the deconvolution itself, I think it's only the beginning. What we can do with these techniques is completely unclear. We are also to be, here we assume that the training set is completely representative. And this is also something that you have to understand what it means in practice. And the second point also, which is important, is the PSF in the deconvolution part were assumed to be perfectly known. And how these deep learning techniques will behave if the PSF have some errors, which will be the case in practice. This is also something that has to be investigated. Thank you.